In the previous lectures, we discussed about few special purpose diodes like Zener diode, Varactor diode, and tunnel diode. In this lecture, we will discuss about silicon controlled rectifier, which is one of a thyristor, and you have in your syllabus as under special purpose diodes. What do you mean by thyristors? We are able to see 4 layers of PN layers here. So actually, if you take a PN junction, how many layers are there? It consists of 2 layers and 1 junction. If you go for a transistor, transistor has 3 layers, emitter, base, collector regions, but you have 2 junctions like emitter junction and collector junction. Now, thyristors are the devices or components which consists of more than 3 layers and more than 2 junctions. They come under the thyristor family, like what we have listed here, like diac, triac, silicon control rectifier, so SCS, GCS. You have number of thyristors where under which you have SCR under your syllabus. So these are few thyristor components what you see. You have an SCR2 here. So any device which consists of more than 3 layers and more than 2 junctions, you can consider them under thyristor family. Now let us go for silicon controlled rectifier, what you have in your syllabus. So silicon controlled rectifier, actually as it is a thyristor, as you see in the picture, in the construction module and in the representation too, it consists of 4 layers, PN layer. The p-type material, what you see, is connected to the anode terminal. The n-type material is connected to the cathode terminal, and the p layer, which is nearer to the cathode region, that means cathode terminal region, is connected as gate terminal. So you are able to see the symbol at the end of this PN junction, where you have 2 terminals, anode and cathode, similar to a diode, where it can work like a rectifier. Here, as in PN diode, you may not use germanium and silicon for constructing this diode. Only you will be preferring silicon. So this is called a silicon controlled rectifier. The rectification can be controlled. We can see in the characteristics how we are going to use the silicon controlled rectifier. Now, so as we have mentioned, it consists of 3 layers, PN, and 3 junctions, and you name it as J1, J2, and J3. So these are the 3 junction names what you will be using for silicon control rectifier. Let me call it as SCR. So this SCR consists of 3 junctions, J1, J2, and J3. Now, this 3 layers, you can split them and treat it as 2 transistors like this. So the first layer, PNP, you are splitting the second 2 layers, and the first P layer is the anode terminal. You can treat it as a PNP transistor. Now coming to the second part, NPN. So this 3 layers will be considered under one more transistor. So you can consider the SCR as a 2 transistors which are connected as shown in the picture. So what you see here, the gate of the second transistor is connected to the collector terminal of the first transistor. Similarly, the base of the first transistor is connected to the collector terminal of the second transistor. So you are able to see the 2 transistor version of SCR. Before going into mathematical derivation of this transistor version of SCR, first let us check how it will operate by applying the voltage. How you are biasing it, that means first you have known about the construction, then the circuit symbol. Now we have to bias it. What type of voltages we can bias? Let the gate voltage be the control voltage. The other 2 terminals are anode and cathode. So let us apply a positive voltage to anode terminal with respect to cathode, a negative terminal with respect to cathode, and let us check how this SCR will operate. What happens at junction J1? What happens at junction J2? What happens at junction J3? Okay. So let us see the modes of operation. Actually, when you connect a negative voltage to the anode terminal, you call that it as you see in the first picture, You call it as reverse blocking mode. Reverse blocking mode is indicated in this picture. We will see each and every mode of operation again. Just for a overall summary type, you are just indicating this circuit where you are applying a negative voltage to the anode terminal with respect to the cathode, and you have not given any gate voltage till now. It is 0, so the terminal is kept open, so you have not applied any gate voltage. Only initially you have applied a negative voltage to the anode terminal with respect to cathode. Then you name the transistor, that means whatever the SCR is there, that is working in reverse blocking mode. Now, if you apply a positive voltage to the anode terminal with respect to cathode, then you say initially the SCR is working in forward blocking mode, and continuously as you increase the voltage at a particular instant, it will turn to forward conduction mode. How it happens, we will check it. We will go with each and every mode of operation. We will go how this characteristics is derived from this operation. So let us go with the reverse blocking mode first. When you say reverse blocking mode, as you apply a negative voltage to the anode terminal, what is happening? When you apply negative voltage to anode, that means the first P layer is applied a negative voltage. Negative to P means it is reverse biased. When it is reverse biased, junction J1, at the junction J1, you see a depletion layer. It is similar to a reverse biased PN junction. Similarly, this negative voltage is applied to the second layer, a negative value to N-type region. So the second junction is forward biased. Next, same positive voltage is applied to the cathode terminal. So positive to N means again it's reverse biased. So junction J3 is reverse biased. So from this application of voltage, what you are able to see, you have applied a voltage negative to anode terminal with respect to cathode, because of which J1, J3 are reverse biased, but J2 is forward biased. Is there any conduction when J1 and J3 is reverse biased and J2 is forward biased? Can we see current conduction through the device? Let us see. If J1 is reverse biased, you will not have any current through it. But practically speaking, you have some reverse leakage current. So as you see in this characteristics, in the characteristics picture, a very minute current is flowing through the device initially, from 0 volts to -1 volt, -2 volts, -3 volts. So you are continuously applying it. So because of that, you are able to see very lesser current through it. Because though J2 is forward biased, J1 and J3 is acting like an obstacle where it is not making the current to flow through the SCR. So though J2 is forward biased, J1, J3 is reverse biased, it is stopping the current to increase. So you will have a very lesser amount of current where you will have only the reverse leakage current. Let us consider you have further increased the reverse bias voltage from -1 to -10. So you have reached some voltage of -10 also. At that point, junction J1 and J3 will break down, and as it's break, that means when the junction breakdowns, you see a heavy flow of current. That breakdown current will be added to the forward bias current of J2. Because of that, you will see a heavy flow of current here at a sudden. So you see in the reverse bias, until breakdown of J1 and J3 is occurred, you will not see any heavy current through the device, and you name it as a reverse blocking mode of SCR. So this is in the reverse bias characteristics of SCR. Let us go to forward bias characteristics. When you apply a positive voltage to the anode terminal with respect to cathode terminal, junction J1 is forward biased, junction J2 is reverse biased, junction J3 is forward biased. Now, when J1 and J3 are forward biased, J2 is reverse biased. Though current is flowing at J1 and J3, but J2 is resisting the flow of current. It will not allow the current to pass through it. So still, though you have applied in the forward bias mode, the current is very, very lesser. So you name it as SCR is in forward blocking mode. But when you go on increasing the same applied voltage, positive anode voltage, you see at a particular breakover voltage, which is termed as VBO. So at a VBO voltage, you see that there is a sudden trigger in the current value where the voltage will be dropped, and at a sudden the current will increase, which will turn SCR from blocking mode to conduction mode. The current where at which you will see the heavy flow of increase of current, you name it as latching current or holding current. So at that point, all these things you are considering at Ig is equal to 0. You have not still applied any gate current. If you want to turn it on, that means from offstate you want to turn it on sooner, then you will be applying a gate voltage as shown in this picture. So you are applying a gate voltage, so let it be Ig1. So you will see a dotted line curve, what you are able to see in the forward conduction mode. So you will have, with the increase of gate current, you are able to trigger the SCR from off state to on state, forward blocking mode to forward conduction mode. So you will turn on the SCR, and you may say it has moved from blocking mode to conduction mode. You say this in the blocking mode, it has forward leakage current. After breakover voltage VBO, you see a latching current or holding current where it will turn to forward conduction mode. You say it as SCR as turned from off state to on state. So this is the complete characteristics of SCR. This is a 4-layer PN layers. You will have a circuit symbol like this. So when you reverse bias, that means when you apply a negative voltage to anode, you will see this type of characteristics, where at breakdown voltage, you will see heavy flow of current. So this mode of operation, you have named it as reverse blocking mode, where you will see very lesser leakage current until breakdown voltage. In the forward blocking mode, though you have applied a positive anode voltage, the current is very lesser until breakover voltage. Once it reaches breakover voltage, at that particular knee voltage, you see a sudden increase of current and turns the SCR from off state to on state. So this is about SCR characteristics. So this is showing both with gate voltage 0 and gate voltage a positive value. If it is 0, you will get a curve for Ig is equal to 0. If it is increased with Vg value, Ig1, Ig2, Ig3, with the applied gate voltage, you are able to see the SCR has triggered from off state to on state. Okay, so this is about SCR and its characteristics. Next to this is 2-transistor version of SCR. As we have already discussed, this is split into 2 transistors. One is PNP transistor, one is NPN transistor. Base of the transistor Q2 is connected to the collector terminal of transistor Q1. Base of transistor Q1 is connected to the collector terminal of transistor Q2. So you can clearly say that they are connected means base current is equal to base current of transistor Q2 is equal to collector current of transistor Q1. That means T1 or Q1, whatever it is. You can represent the transistors as Q1, Q2 or T1, T2. So the second transistor IC2, collector current of second transistor, is connected to the base terminal. So it is equivalent to the base current of the first transistor. So the current to the cathode terminal now will be IK if you treat it as Ig plus Ia. Actually, we know the common general equation of transistor for PNP or NPN. IC is equal to alpha IE plus IC naught. So we will take the same equation, club them both to get both the currents, and we will indicate it as anode current, where it is alpha 1 IB means IA plus ICB naught. Second current is IA into alpha 2 into ICB naught plus IG value, gate current value. So you want IA, so it is the anode current. Rearrange the equations from this 2-transistor version. When you apply an anode voltage positive with respect to cathode, you will be able to derive what is the anode current with the equations of both the transistors. So here what you are deriving, why we need 2-transistor version? If you want to derive the current through the silicon control rectifier, then you are treating them as two transistors connected, where collector is connected to base of another transistor, and you are able to derive the equation of SCR, anode current, with the basic transistor equations, where I is equal to alpha IB plus IC naught. IC naught is the reverse saturation current. So in the place of input current, you are taking it as IA, which is anode current. IE place, you are replaced with the IA. Rest of the thing is same. Okay. So this is about SCR, special purpose diode. In the next lecture, we will discuss about UJT, which is uni junction transistor.